to do problems on internal forces. We have solved last time some problems on shear and bending diagrams. So I will continue with these problems. Draw the shear and bending moment diagrams for the following beam. So here we have a rectangular beam. The beam is subjected to a rectangular force on it, and it's supported by a pin and a roller. I think last time we covered the shear. I will do it again in summary. So here, since you have a symmetry in your beam, because you have a distributed load that is symmetrical with respect to the center. Also, you have supports along Y, you have symmetry in the supports because both develops Y reactions, and no X force, so no external, no reaction along AX. Then we can say that in this case, because of the symmetry, we can directly just find the shear variation between A and B and deduce it between B and C. And this is what we did last time. So we said first that since we have a positive reaction at A, so we start from a positive value of plus 70. Then, because we have a constant distributed load equals to 40 and it's downward, then the shear is linear decreasing. So here, in the exam, if I ask you to draw the shear and bending moment diagram, you just should do some of the following annotations. You put the main points. So here I have 70 kilonewton. Since here it's a linear variation, you just specify the slope. So here's the slope is equal to minus 40. And from A to B, I have that variation. Why I stop at B? Because I have at B a concentrated force, so I will have a jump at B. Okay. So from A to B, the variation of shear is equal to the area under this rectangle. This area is equal to 40 times 2 equals to 80. So I will go downward 80 from a value of plus 70 to a value of minus 10. Okay. Then once I find the 2 points, all I have to do is to join them by a straight line. Now at B, I have an upward jump of plus 20 because I have an upward force. So I will go from minus 10 to plus. Here, if you want, because of the symmetry, you can just continue your graph by taking the symmetry with respect to this point. Okay, so here, here it's minus 10, here it's plus 10, and then since here it's plus 70, here it should be minus 70, and then I take the linear variation and I am done. The shear is, if you want, symmetrical with respect to point O, because if I have a positive value here, I will have a negative value on the other side. Why? Because as we said last time, if you have, due to the convention, if you do a cut at a certain point, so if I do the cut here and I do a cut at the opposite side, okay, here when I take this part, the shear should be is positive when it is downward to rotate clockwise about the end of the beam. On the other hand, here when I do the cut and I leave this part, the shear should be upward. This will give me opposite signs from each side. Okay, so here if you put like this is the middle due to the symmetry effect. 2 points symmetrical with respect to the middle will have opposite values of shear. Now concerning the bending moment, it is the opposite, because look, the bending moment in this cut is like this, while in this cut it is like this. So when you compare with respect to the symmetrical line, it's a mirror. Okay, So it's a mirror with respect to this line for the moment, while for shear it's opposite sign. This is why here, when we draw the bending moment, it will be symmetrical with respect to this axis, which is the opposite case in case of shear. Okay, so when you have a symmetry in your load and also a symmetry in your support, then you can say that you can draw the half of the variation and deduce the other half. Okay? Now, for the bending moment, in order to draw it, you should look at two things. You should look at your beam to see if I have a concentrated couple or if I have a fixity. So whenever I have a concentrated couple, it will cause a jump in the bending moment. Here I don't have any concentrated couple, so no jump in the bending moment. And since here at A and C I have no fixity, no couple, then I will start my bending moment by 0 and I should end by 0. So here, first I start by a value of the bending moment equal to 0. Then, in order to continue my graph, I should look at the variation of my off-shear. Okay? So to start with, shear represents the slope of the moment. So here, you start by a positive value of 70 kilonewtons. This means here that you have a positive slope of 70. So you can just annotate your graph like this. So here, phi equals to 70. Then, a very important point is the one for which shear is 0. Because when shear is 0, this means that I have a maximum or minimum in the bending moment. Okay, because V represents the slope of M. So I have a horizontal slope. So what will happen here, as you can see, V is decreasing in a positive way. So you will have a positive slope that is decreasing, which will give you a downward concavity. Also, you can expect this because W is downward, so the concavity of M is downward, until reaching a slope of 0. Now, to determine the value of the moment at this point, we should find the variation of delta M between this point and this one. It's equal to the area under V curve. So I should calculate this area. Now, to calculate this area, we have here we should find what is the intersection point with this axis. Okay, we can do it by simple geometry, because here, as you can see, you have these two opposed triangles. You can use Taylor's theorem or similar triangles, so it's the same. So you can do that. If you call this length, I don't know it, I will call it x. So this is x, and this distance is known to be 2 meters. So you have 2 from here to here. Okay? From this point to this point, you have 2 meters. And this is x, so the remaining part here, the small part, will be 2 minus x. So this part here is 2 minus x. Now you can apply the concept of Thales or similar triangles. So you can say that the ratio of 2 minus x over x is equal to this length, which is 10, over this one, which is 70. So you can write now that 2 minus x over x is equal to 10 over 70, so 1 over 7, okay? And then you calculate the value of x. Once you get the value of x, so here we will get 1.75 meters.
Doctor, it's 1 over 70.
لا هي 10 over 70 يعني 1 over 7. Okay?
Okay, yes, doctor.
I did the simplification. So now, once I calculate the value of x, I will get x equals to 1.75. Now I can calculate the area of this triangle. Okay, so the area here, you can just annotate like this, and this area is equal to, I have 70 times x over 2, so it is 70 times 1.75 over 2. This is the area of the triangle. Then my moment should increase to this value. Okay, so I will get a value of 61.25. Since my moment starts from 0, then my moment at this point, okay, will be equal to the value of the area, because I do 0 plus a, I get that my maximum moment is 61.25. Now, after this point, my moment will start to decrease because v is negative. So v is negative and linear, then the moment is a second degree parabola decreasing here. Okay, so just you can say here that this is a second degree parabola because v is linear. And the concavity, you can deduce it from omega. Since omega is negative, okay, because the second derivative of moment is equal to omega, since omega is negative, then the concavity of m is downward. So this is a second degree parabola. And now to know how much the moment will drop, you will calculate this area, the area of this triangle. Okay, this area is equal to, so here I will call it A2. So A2 is equal to, I have 2 minus x, which is 0.25. So 0.25 times 10 over 2. Okay, so this is equal to 1.25. Therefore, my moment will drop from 61.25 to 60, because this value is equal to the previous value, 61.25, minus A2. So this will give us 60. So because it's 61.25 minus 1.25. So we got that the moment here is 60 at point at the middle. Now no need to continue, because from symmetry I can stop here and say let us draw the symmetry to the vertical axis, because as I told you, when you have a symmetry in your loading and in the y reaction in supports, okay, then you can say that I have symmetry in moment with respect to the vertical axis and symmetry in shear with respect to the middle point. Yeah? So here just I have to say that from symmetry I can draw the second part, and I get the value of my moment, the graph of my moment, bending moment. Any question on how we did the graphs? Okay. So let us continue with the problems. Draw the shear and bending moment diagrams for the following beam. So here also, always same concept, okay? So here in for this beam, we have it is subjected to several forces, okay? We have here a distributed load. So let me put it. This distributed load is 20 kilonewton per meter. And you have here they directly gave the reactions, okay, but here you might have, for example, a pin here. So let's say this is a pin, for example, and this is a roller at E. So you should calculate. In general, we don't give you the reactions. You should calculate them. So a first step will be to calculate the reactions at B and E. Here, for example, in general, you can just calculate the reaction at B, okay? Because you don't need the value of reaction at E to complete your graph. But in general, I advise you to find it just for verification of your results, because at the end value of your shear should be equal to the opposite of the reaction at E. Why? Because we consider that just at E, just after E if you want, or just E is the transition. When you have a concentrated force, you have a jump. So just at E, you will have a jump to 0. Okay, so you can verify if you calculate the reaction here, it's 40. You should make sure that the end value of your shear is -4. So I advise you to find it just for verification. So now, to start with, if not given, of course, we should find B, Y, and EY as a first step. So you are used to do this. For example, to calculate BY, all you have to do is to do sum of moments about E. Always try to reduce the time. I teach you several methods for you to select the easiest one. So in a problem, ask yourself, what do I want? No need to do everything if you can do it in a shorter way. Okay, so here, for example, if just you want to get By, just do sum of moments about E. Okay, so when you do sum of moments about E, the only unknown will be By. You can get it. If I want to do it, I have here a rectangular load. I can reduce it. I can represent it by an equivalent force equals to 20 times the distance, which is 4. So 20 times 4 equals to 80. And we have here that we can select a positive direction for the moment. So let's say, just let me check the questions. Rami, is it okay to always take the shear to be upwards and let the sign determine the true direction? No, Rami, it's not. You cannot take always the shear upward, because when we do the convention, it depends on the part you consider. When you do a cut, okay, when you do a cut in your beam, you can work on the left part or you can work on the right part. Okay, you should obtain the same result whatever is the part you worked on. This is why we come up with the convention. So if you decided to work on this part, the left part, then when you draw your graph like this, you should take the shear as downward to rotate clockwise about the other end. Okay, and then get the value of B. This value, if it's positive, then on your shear graph you put a positive value, and in case if it's negative on your shear graph you put a negative value. Okay, so you cannot change the convention, because if you change the convention, how you decide which sign to take? This will lead to confusion, because if you do the analysis on the other part and you decided to put the shear also downward positive, okay, you will get opposite results here and here, because by action reaction this should be opposite. This is why we come up with a convention. If I'm working on the left part, I take B positive to be downward. If I'm working on the right part, I take the convention of shear to be positive upward. Okay.
This convention is regardless كيف مقسمين الفورسز.
أكيد it's regardless.
Okay, thank you.
Okay. هونيك وقتها أنا لأنه أنت كيف ما كانوا الفورسز بس تعمل كات فيك تاخد الليفت أو الرايت بارت. شو ما أخذت you should get the same result for V. إذا بتاخدها V positive in both cases حيطلع لك opposite results إذا بتاخد الرايت section أو الليفت section. أوكي. ساعتها أيها بتحط على الدياجرام. You should have the same value in both cases. Okay.
Yes, okay, thank you.
The plus 40 on A and C. Ah, you mean which one here? This one? Oh, let me change. The plus 40 هي الاريا guys. هن شوي it's misleading. Plus 40 هي الاريا. When you do the shear graph, you should determine first at B you have a concentrated force. So from A to B, you should take the area of this part. The area of this part is 20 times 2. Okay, this is why I should go downward a value of 40. Okay. يعني هن لازم يحطوها in another way. They should put it like this. إنه area of part 1 equals to 40. And why they divided it into two parts? Because you have the concentrated force in between. Okay. And area of part 2 also is equal to 40. I will need it to draw the shear graph. Okay.
Doctor,
Yes.
بلخبط على طول whenever I have a distributed load in the middle like B we have the 100.
Yeah. What's the problem?
Like,
Can you repeat the question, Marisa? I didn't understand.
no, I'm Karen.
Karen. Yes, Karen.
Yeah. Whenever I have a distributed load and in the middle يعني I have عادة a force طالعة مثلا.
Okay.
مثل البي هون مثل in this case I don't know how to think about it.
Okay. أنت whenever you have something يعني بس يكون في لو ما كان في البي واي you take it as one distributed load. Okay. بس لأنه أنت عندك البي واي you should do the analysis first from A to B what it's happening. At B you stop, you do a jump equal to the force. And after B you continue عادي إنه from B to C I have a rectangular distributed load. Okay. يعني here
Yes,
first, from A to B I have a rectangular load. The area is 40. I should go downward 40. Okay. So I start, since at A I don't have any concentrated force and no reaction, I start from 0 at A. From A to B, I have a constant value of omega. I don't have any concentrated load, so no change from A to B. I do a linear variation because since omega constant, V will vary in a linear way, and the slope of V is phi equals to minus 20. Okay, now I should stop at B because I have a concentrated force. Whenever I have a concentrated force, it will cause a jump. Since it's a positive force, it will cause an upward jump. So I go from minus 40 here because here it's minus 40 because the area is equal to 40, and I should subtract from 0 minus 40 because omega is downward. Okay, so the value here is minus 40. Then, because of the concentrated force at B, which is plus 100, I have a positive jump of plus 100. So minus 40 plus 100 will give me plus 6. Now, from B to C, okay, again I have a distributed load that is rectangular. So the shear will be linear. So the slope here will be minus 20. And in order to know how much I have a decrease, I calculate the area. The area here is 40. So I should do 60 minus 40 to get the final value here, which is 20. So 60 minus 40 equals to 20. Okay. Then at point C, I have also it's a concentrated force that is downward. So I should move, I should do a jump, a downward jump of 60 from 20. 20 minus 60 will give me minus 40. Okay. Now, after this, from C to D, I don't have anything. At D, I have a couple, but the couple will not affect the shear, it will affect the bending moment diagrams. So here, since I don't have any variation in load here, in concentrated or distributed load as forces, then no variation in my shear. So I will have the shear constant here in this part equal to minus 40. And as a verification, I can see that at the end of my beam, the value of shear is the opposite of the reaction. The reaction at E is plus 40, and the value of shear just before E is minus 40. So just at E, minus 40 plus 40 will get me back to 0. Okay? So this is for the shear diagram. Now, I will do the same analysis to draw the bending moment diagram, and I should look at if I have any couple. Here, yes, I have a couple at D. So I should keep in mind that because I have a couple at D, and it's a clockwise couple, the clockwise couple will lead to a positive jump. So at D, I should do a positive jump. So remember here to do a positive jump for the bending moment. So now I will deduce the bending moment from the shear diagram. As I told you here, no fixity or no couples at the extremities. This is why I will start from 0. And to verify, I should end also by 0. So let us start. First, you have in this part from 0 to 2 meters, you have that V is a negative, so the moment is decreasing. And because here I have linear variation, okay, so since here it's linear, then the moment is a second degree parabola. Okay, now after this, I have the variation of V will give me the slope of M. So initially V is 0 here. So since V is 0 here, the slope of M is horizontal. Then V is decreasing until reaching minus 40. So the slope here will decrease until having a value of minus 40 here. So you can just put the extreme values. So this is 0 slope. So here I have phi equals to 0, horizontal tangent. And here I have phi equals to minus 40. So please, if I ask you to draw the shear and bending moment diagram in the exam, you should put these details. Okay? Just when you put these details, I will see how you did it. And here, for example, you should put that the area is equal to the area of this triangle is equal to 2 times 40 over 2. Okay, so it's 40. This is why delta M from this point to this one, okay, will be minus 40 because V is negative. So since I'm starting from 0, then here I should have a value of minus 40 for the moment. Concerning that it's concave or convex already, because here, look, always for the bending moment, you can know it from this equation. You know that the second derivative of bending moment with respect to x is equal to omega of x, okay, equals to omega x. And in this problem, you have that omega is negative. It's a downward rectangular force. Since omega is negative, then the concavity of M should be down. Also, you can know it from the variation of slope. So if you follow the slope variation, okay, you will get a downward concavity. Okay. So here then, what will happen here when the shear will change suddenly, in the bending moment, I will not have a jump, but I will have sudden change in slope because V represents the slope of the moment. So the slope just before this point was minus 40. while just after it is 60. So you have a jump in slope from negative to positive value. So here you can represent it by this. You put here, I have a new slope. This slope here is phi equals to plus 60. So now I have V becomes positive. So I have increasing moment now. But the concavity will still be downward because if you omega is negative, and also if you follow the variation of slope, okay, from variation of your slope, you have that the slope is positive but decreasing. So because the slope is positive decreasing, if you represent its variation on your graph, you will see that you will obtain a downward concavity. So like this. Okay. Now, at this point, the slope will be equal to the value of shear here. The value of shear here is 20. So you can just put here that I have, it's also a second degree parabola, and the shear here is, the slope here is equal to the value of shear, it is 20. Now, in order to know what is the value of bending moment here, all you have to do is to say that the delta M from this point to this one is equal to the area under this graph. And this area can be divided into, it's a trapezoidal area, okay? If you know the formula for a trapezoid, you can just do the middle height here times the base over 2, okay? So here the middle height is between 20 and 60, it's 40. So it's 40, okay, times the value of the height, اللي هي 2. Okay, so here in a trapezoid, you do the middle height times the base. This is the area. 40 times 2 equals to 80. Okay, and to find the middle height, you just do 20 plus 60 over 2. Okay, so then I should go downward a value of, sorry, I should go upward. Why upward? Because the shear is positive. Okay, when you have a positive shear, then your moment is increasing. So I should go up a value of plus 80. So since I was at minus 40 and I do plus 80, then I get plus 40. So plus 40 is minus 40 plus 80. Then I get the value of my bending moment at this point. After this, again, I have a variation, a sudden variation in shear, which will give me a sudden variation in slope. So I go from a slope of 20 to a negative slope of minus 40. So the slope here is minus 40. Phi equals to minus 40. And since it's a constant shear, so M is linear. Okay, so I can say now that I should remember that I have what I have here, a couple. Don't forget the couple. Okay, so always look not only at the shear diagram, you should look at shear diagram and at your distributed at your beam to see the load on it. On your beam, you have a couple at this point, so you should pay attention to do a jump at this point. So first, because I should do the analysis, what is happening from this point to this one? From this point to this one, I have a linear variation of moment because V is constant. And since it's negative, M is decreasing. To know how much it's decreasing, I get the area of this part. The area of this part is 40 times 2. And I do, which is 80, I do minus 80 because V is negative, so it's a decreasing moment. So now I can say that I have a linear decrease from plus 40 to minus 40 because this value here is equal to 40 minus 80. So I get minus 40. Now, at this point, I should stop because I have a clockwise couple. The clockwise couple will give me an upward jump. Since I have the clockwise couple equals to 120 and the value was minus 40, so I will have an upward jump from minus 40 to 80. So 80 corresponds to minus 40 plus 120. Minus 40 plus 100. Okay, and then just let me. In the exam, guys, if I give you a beam, it will not be, it will be a small one. Don't worry about it. The time is well studied. Okay. Of course, I will not give you a very large problem. I give you a small, a beam subjected to not a lot of variable loads. So you can draw the diagrams. But yes, the concept is the same, and you should put these